we start with the solution of state equation, that is for force system. In this we will study classical approach, then Laplace transform approach, and then we will see one example. Now about the classical approach. Last time we have seen state equation for unforced system, that is last time we have seen x dot equal to ax, this is a plant, and x of t equal to e raised to at x of 0. This part we have seen last time. So, this is unforced system. Now, today we have to see the force system. There is a force is applied. Therefore, the plant which we are taking, that is x dot equal to ax plus bu. Now, for this plant we required a state equations. As I told last time, the state equation plays a very important role, because as the states are playing an important role in the complete part of the system, how the state changes from initial time to final time, and as well as at t tend to infinity, that information is very much important. And in case of unforced system, we have seen that the complete state equation depends on a matrix. But now we have state space model in terms of ax plus bu, definitely their state equation depends upon the B matrix. Now let us see, when we derive the state equation, in this case can we get the term of B or not. Now we start developing the state equation for a force system. So this force system can be written as x dot t equal to a x of t plus b into u of t, where x of 0 equal to x 0. Now how will you proceed further, because finally we want x of t. So what we can do, we will multiply this equation by e raised to minus at to both sides. So multiply this equation both sides by e raised to minus at, so we will get e raised to minus at x dot t minus a x of t equal to e raised to minus at b into u of t. If you make a differentiation of e raised to minus at into x of t, now we will differentiate this equation and we will see the result, and then we will correlate this with these equations. So you now we differentiate these equations. So we will get e raised to minus at into x dot t plus x of t into minus a of t. That is what we have done, e raised to minus at, the first term constant, then differentiation of this x of t, x dot t plus first term, the differentiation of e raised to minus at is e raised to minus at, and this constant term minus a we have multiplied by this, and now you will find that this equation and these equations both are the same thing. Therefore, the next step we can write down as the differentiation of e raised to minus at into x of t equal to e raised to minus at into b into u of t. Now this equation we have done, that means what we have done here. First of all, we have multiply e raised to at both sides. So here e raised to at, here e raised to minus at, a b u of t. Then this equation we have written like this, and finally this differentiation has come, e raised to minus at b into u of t. Now our aim is to determine x of t. Now here differentiation has come, so the best option is that we integrate this equation. So if you integrate equation, definitely some term of x of t will get. Therefore, integrating both sides from 0 to t, so if you integrate both sides 0 to t, that is differentiation of du of dt e raised to minus at into x of t equal to 0 to t e raised to minus at b into u of t. Now you will find we get differentiation one integration. So, integration and differentiation is there, but it will nullified, that remaining is e raised to a t into x of t, but the limit will come, that is 0 to t. That means that this equation can be written as e raised to minus a t x of t minus x of 0 to t e raised to minus a tau b u tau d tau. So, now we got e raised to a t x of t minus x of 0 to t e raised to a tau b tau d tau. So, now how to move further? So, what we have done, we will remove this x of 0 on the right hand side and then try to use the concept of e raised to minus a t in the right hand side and see what result will come. Now, after this equation, what we can do, we will multiply it by e raised to a t plus a t both side. So, what happens, this whole term will be nullified and therefore, we can write down the equation as x of t equal to e raised to a t to x naught plus 0 to t e raised to a t e raised to minus a tau b of u tau d tau, and therefore, finally, this x of t equal to e raised to a t x naught plus 0 to t e raised to a t minus tau b u tau d tau. So, here we have got the state equation, this is the state equation. The state starts from 0 up to time t and we have got these equations, and finally, we found that this state equation depends upon a as well as the b. But now sometimes it is found that we have to start the state from t0, not 0, actually t0 to t, then how to write down these equations? Now, we write down the equations. So, if the initial state start from t equals to t0, we can write down the equation as x of t equal to e raised to a t minus t0 plus t0 to t e raised to a t minus tau b u tau and d tau. So, here limit from t0 to t, and you will find that this particular portion, that is called unforced response, and this particular portion is called forced response, and complete state equation depend upon A matrix, B matrix, input, and therefore, this is the state equation we have determined. So, this is the one classical approach which can be used, but as I told you that as the order increases, sometimes the calculation wise is quite difficult. Therefore, we need an approach so that we can easily determine the x of t. So, best approach is the Laplace transform. Last time we have seen for a unforced system a Laplace transform approach. So, here also we can use this concept of Laplace transform approach for the forced system. Now, we start deriving the state equation using Laplace transform approach, that is we can write down the equation as x dot equal to ax plus bu. Now, what we do? We have to take the Laplace transform for these equations. So, taking Laplace transform both sides, we can write down as x of s, x naught a into x of s plus b into u of s. Now, we can take x of s on left hand side and then we can get the equation as si minus a into x of s equal to x naught plus b into u of s. Now, this x of s equal to si minus a inverse x naught plus si minus a inverse b into u of s. that is x of s equals to Si minus A inverse x of 0, Si minus A inverse B into u of s. Now, we have got x of s, but we have state equation, definitely it is in terms of time domain. So, to get the time domain, what we can do? We have to apply inverse Laplace transform to this equation. Now, we apply inverse Laplace transform to these equations. So, we can get it as x of t equal to Laplace inverse of Si minus A inverse x naught plus Laplace inverse of Si minus A inverse B into u of s, and here we can write down this as e raised to at into x naught plus Laplace inverse of phi of s into b u of s, that is here it can be as phi of t into x naught plus Laplace inverse of phi of s b into u of s. That means, finally, this x of t equal to phi of t into x naught plus Laplace inverse of phi of s b into u of s. So, you will find that even mathematically also, or by deriving this equation, we have reached easily the x of t, and this x of t is based on the Laplace inverse of Si minus A. This concept of Si minus A inverse we have used in diagonalizations. So, it is useful in a various type of modeling, and this getting inverse we have used two different approach. One is the classical approach, where we have to take adjoint and determinant, and another simple method I have to explain earlier, that is about the Leverrier algorithm. So, you can use any of the method, but as the order increases, it is better to go for the Leverrier algorithm to get the Si minus A inverse. But if the order is small, say second, third order, you can use the classical approach to get the Si minus A inverse. That means, finally, this x of t it depend upon this phi of t into x of x0, and this phi is b into us, and this portion it is consists as forced part, and that is the unforced part. So, now based on this concept, now we try to solve an example and see what value of x of t will get. Now, our example is, we have to obtain the time response, of the following system. And our example is x dot equal to 0, 1, minus 3, minus 4, x 0, 1 into u, y equal to 1, 0, x, and your u of t is basically a unit step function. So, u of t is unit step function, and initial conditions that is x1 of 0 equals 0 and x2 of 0 equals to 1. This is the initial condition. Now, this is your state model, and our purpose is to get the x of t. Now, which method we can apply? So, you can use any of the method, but now we go for the Laplace transform approach. So, we have seen earlier how to get the y of t, or sorry, x of t, how to, that is the x of t can be written as Laplace inverse of Si minus A inverse x naught plus Laplace inverse of Si minus A inverse B into u of s. That is basic calculation involvement here, Si minus A inverse. So, A is this one, A matrix is 0 1 minus 3 4. So, first of all we write down Si minus A. So, we write down this Si minus A equal to S minus 1 3 S plus 4 Si minus A. Now, to get the Si minus A inverse, we can write down this as Si minus A inverse, that is equal to adjoint of Si minus A divided by the determinant of Si minus A. And how to define the adjoint of Si minus A? So, adjoint of Si minus A equal to cofactor of Si minus A transpose. First of all we determine the adjoint of Si minus A. So, here we can write down as Si minus A, that is just here. To get the cofactor, so here for S we will get S plus 4, then for this S plus 4 we can write down S. Then for this minus 1 position, so here it is in odd terms. Odd means here first row first and column second. So, whatever elements we will get, we have to connect a minus sign. So, here minus 1, so with to this we will get 3. So, we have to use a sign of minus 3, and here for this portion, for the first 3, the minor is this minus 1. Again it is odd term, that is row is 2, column is 1, so it is 3. So, odd is there, we have to use connect a minus sign. So, here we will get minus 1. So, minus of minus 1 equals to plus 1. So, we will get it as like this. This is transpose, and therefore, we can write down this equation as S plus 4 1 minus 3 and S. Now, coming to the determinant. The determinant of Si minus A. So, just see here, that is S minus 1 and here S 3 S 4 3 S plus 4. Now, the determinant of Si minus A equal to S square plus 4S plus 3. Therefore, finally, the inverse, that is Si minus A inverse, we can write down as S plus 4 minus 3 1 S divided by S square plus 4 S plus 3. And finally, this equation can be written as S plus 4 divided by S square plus 4S plus 3 1 upon S square plus 4S plus 3 minus 3 divided by S square plus 4S plus 3, and here S divided by S square plus 4S plus 3. Now, this we have written, and now our main purpose is to get this Si minus A inverse x of 0, that is Laplace inverse. Therefore, the equation we have got, we have to use the Laplace inverse, that means the Laplace inverse of Si minus A inverse. So, this equation will get in terms of x of t. So, if you see this S plus 4 S square plus 4S plus 3, it is not possible to calculate the inverse directly. Therefore, this equation we have to convert into partial fraction expansion. Last time we have seen how to convert into partial fraction expansion, and then we can go for the Laplace inverse. So, particularly if you say S plus 4 divided by S plus 3 S plus 1, if you convert this into a partial fraction expansion, we will get the result as minus 1 divided by 2 S plus 3 plus 3 by 2 divided by S plus 1. And now for this particular portion we have to calculate the inverse, and moreover the inverse of this is not dependent upon this, therefore individually we can calculate the inverse of this. So, Laplace inverse of this we can write down as minus 1 by 2 e raised to minus 3t 3 by 2 e raised to minus t. Now, this term we have taken into consideration. Now, about this term, this and this. So, we can write down for all these terms the Laplace inverse as 1 by s plus 3 s plus 1. This can be written as minus 1 by 2 s plus 3 plus 1 by 2 s plus 1, and after solving this we will get 1 by 2 and here 1 by s plus 3 e raised to minus 3t 1 by 2 e raised to minus t. That is, this we have come into partial fraction expansion like this, and then we have taken Laplace inverse and we have got this. Now, next, so after completion of this part we can write 3 upon s square plus 4s plus 3 at this part. This s plus 3 s plus 1 is same thing. So, here s square plus 4s plus 3 here minus 3 like this. So, for this we can get the result as 3 by 2 s plus 3 minus 3 divided by 2 s plus 1, and after solving this we will get 3 by 2 e raised to minus 3t minus 3 by 2 e raised to minus t. So, we have taken care of this portion, and finally we want the Laplace inverse of this particular part. Therefore, we can write down this as s divided by s plus 1 s plus 3. So, if you convert this into a partial fraction expansion you will get 3 by 2 s plus 3 minus 1 by 2 s plus 1, and if you solve it you will get 3 by 2 into e raised to minus 3t minus 1 by 2 e raised to minus t. So, all these individual transfer functions we have taken into consideration, we have done partial fraction expansion, and then we have applied the inverse Laplace, and now we have got e raised to at. But our main problem is concerned with this si minus inverse b u of s. So, this part we have got, and but for this particular part we have to multiply it by x naught, and then we think about this portion. So, finally, all these 4 transfer function we can write in this final matrix form as minus 1 by 2 e raised to minus 3t plus 3 by 2 into e raised to minus t, 3 by 2 into e raised to minus 3t minus 3 by 2 into e raised to minus t, then here minus 1 by 2 e raised to minus 3t plus 1 by 2 e raised to minus t, 3 by 2 into e raised to minus 3t minus 1 by 2 e raised to minus t. Now, we can cross check it. See here, this portion is like this. So, we are written here. Now, coming to this portion, minus 3 upon s square plus 4s plus 3, that is 3 by 2 e raised to minus 3t minus 3 by 2 into e raised to 8t. So, you will see here, we can write it here. Then coming to this portion, first part s plus 4 divided by s square plus 4s plus 3, that is this one, minus 1 by 2 e raised to 3t plus 3 by 2 into e raised to minus t. So, we have written here, and this one 1 upon s square plus 4s plus 3 we have written as minus 1 by 2 e raised to minus 3t plus 1 by 2 e raised to minus t. So, we have written here. Now, we want x of t that is unforce this portion, that is this part, that is e raised to at, this portion, and we have x naught, the initial conditions. So, initial condition is 0 1. So, if you multiply these conditions here, so what happen if you multiply this with this? So, this portion, left side portion, that is be neglected because 0 will come. So, remaining will be the terms on this one, that is this element and this element. So, finally, the x of t for unforced system we can write down as minus 1 by 2 e raised to minus 3t plus 1 by 2 e raised to minus t, 3 by 2 e raised to minus 3t minus 1 by 2 e raised to minus t. So, we have done the part concerned with the unforced part. Now, coming to the part concerned with the forced part. Now, about the forced part, we have Laplace inverse of phi of s into b u of s. This is the forced part. Now, phi of s, it is s. Now, we write in terms of s domain itself. So, Laplace inverse of s plus 4 divided by s plus 3 s plus 1 1 divided by s plus 1 s plus 3 minus 3 divided by s plus 3 s plus 1 and here s divided by s plus 1 s plus 3 this. And what is the value of b? B, you will see the value of b is 0 1. So, we multiply this by 0 1 and now what is the input? Input is unit step. So, unit step, you know, r t equals to 1, that is unit step input r of t equals to 1 if you make r of s, or here you have we have considered input as u of s. So, r of s into u of s equals to 1 by s. Therefore, here u of s we multiplied by 1 by s. Now, we first of all we multiply all these equations, and after multiplications we have inverse Laplace inverse, that means we have to take inverse, that is Laplace inverse means it is the inverse Laplace, that means we can get the equation in terms of x of t. So, first of all we multiply these equations. So, here Laplace inverse of, now if you multiply it, so again the same thing. So, this multiplied by this, so here we will get a term of 1 by s plus 1 s plus 3, and here also we get the term of s plus 3, and now it is multiplied by s. So, here this particular portion order is 2, the order will increase to third, but whereas this s will cancel with this, and therefore, we can get the equation as 1 by s plus 1 s plus 3 s, and here we will get as s plus 1 s plus 3. Now, we have written Laplace inverse. Now, again we want a time domain equations. So, if you take Laplace inverse of 1 by s plus 1 s plus 3, this can be written as 1 by 3s minus 1 by 2 s plus 1 plus 1 by 6 s plus 3, and then we apply Laplace inverse for this. So, what happens? Inverse for all. So, we can get as 1 by 3 minus 1 by 2 e raised to minus t plus 1 by 6 into e raised to minus 3t. So, we have taken the Laplace inverse of this. Now, coming to the Laplace inverse of 1 upon s plus 1 s plus 3. So, this can be written as 1 by 2 s plus 1 minus 2 s plus 3, and that is inverse Laplace inverse. So, we can get this equation as 1 by 2 e raised to minus t minus 1 by 2 e raised to minus 3t, and therefore, final equation it becomes 1 by 3 minus 1 by 2 e raised to minus t plus 1 by 6 e raised to minus 3t, and about this portion, this one is we got this. So, we can write down as 1 by 2 e raised to minus t 1 by 2 e raised to minus 3t. Now, this part, this portion, This is the force part, and here earlier we have got unforced part, and the complete state equation is a combination of unforced and force. Now all these elements we have to add and we see what final results we will get. So the final results which we will get, that is, if you add this, that is first of all we write the unforced part. So unforced part is 1 by 2 e raised to minus 3t plus 1 by 2 e raised to minus t, and here 3 by 2 e raised to minus 3t minus 1 by 2 e raised to minus t plus, here same this part, this 1 by 3 minus 1 by 2 e raised to minus t, 1 by 6 e raised to minus 3t, and here 1 by 2 e raised to minus t, 1 by 2 e raised to minus 3t. Now this is there, and we have to add this element. So we will find that if you add this particular element, so what we will get, the results which we will get it as 1 by 3, and here this portion will cancel. So we will get 1 by 3 e raised to minus 3t, and about this portion, so 1 by 2 e raised to 80, this will cancel, and here we will get as 3 by 2 minus 1 by 2, that means we will get e raised to minus 3t. So this is the complete response. This part is nothing but the combination of unforced plus force, and this we got final x of t of a state space system when we play force input. So we will find that whenever a system is there where there is environment of A and B, the total response is depend upon unforced part as well as the forced part. But whenever we calculate, whenever we have given a system in terms of unforced part, that the x dot equals to Ax, that is there is only concern with the e raised to 80 and x naught, but whenever a force is concerned we have to take the care of the B, and again we see that as we are involved in the force part, the calculations increases, and again we see that all these things, it is all a mathematics, but it is a very much applications in controller design, controllability, observability, observer, so it has wide applications. Now you will see the references, Nagraj Gopal, Dheeraj Chaudhary, B.C. Ku, and there are many books are available. You can use this book, as we have solved one example. Similarly, you can solve many example, and the most important point, the SI inverse, I have used the concept of the classical approach, but you can also go for the Leverrier algorithm to calculate the inverse. Thank you.